go.
All right, you guys. Let's talk about how to do this. So let's start by reading the question. 12 points. A block is initially at position x equals 0 and in contact with an uncompressed spring of negligible mass. So the spring doesn't have any mass. The block is pushed back along a frictionless surface from a position x equals 0 to x equals negative d, as shown above, compressing the spring by the amount of delta x equals d. The block is then released at x equals 0. The block enters a rough part of the track, eventually leading it to be at position x equals 3d. The coefficient is mu. Let's draw.
Gotta understand what the deuce they're talking about here.
So this is position 0, and here is my block. And it gets pulled back to position negative d.
That compresses the spring.
And there's a spring over here. You know, the spring is here and it's being squished.
Like in the picture.
And then once it's released, it goes all the way to 3D. So 3D.
The spring lets go at 0 and then it goes on its own and comes to a stop at 3D.
Okay. So let's, and what is the question wanting to ask? What's it asking us? On the axis below, sketch and label graphs of the following two quantities as a function of the position of the block between negative d and 3d. You do not need to calculate the values, but the same vertical scale should be used. Okay, so we want to know what's going on between negative d and 3d in terms of kinetic.
Let's not try to answer that question yet. Let's just try to figure out what's going on.
Yeah, so let's take a step back here.
What happens when you compress that to negative d?
Well, when we're right here, do we have any potential energy yet? No, it's not. The spring, remember, the potential energy is held in the spring, and the spring is not compressed yet. So our UG of the spring is going to be 0.
Okay. And then you have to do work compressing it.
I do work compressing it, and then the UG of my spring is going to be maxed out.
Right.
Okay. What do we know about our kinetic energy at this point?
Well, before you let go of it, it ain't moving, so K is going to be 0.
Okay. Now, once we do let go of it, the spring decompresses, and at this very moment, the spring projects the block forward, right?
Yep.
And at this moment, our K is going to be the max. Now,
what happens to the kinetic energy as it goes down to 3D?
Well, so this whole segment right here is a rough segment.
Oh, there's friction.
There's friction. And we know the force of friction is mu times the normal force, yes?
Yep.
And so ultimately, it's going to stop. And so our kinetic energy here at the end is going to be 0. We don't have potential energy. The spring isn't involved anymore.
This
right?
makes sense to me.
Yeah. Okay. So let's write a couple more things down here. We know that work equals force times distance. And
the work you do compressing the spring
is going to have to do with... Okay. So right now we know work is force times distance. We know that the work is stored in the spring.
What's that equation for the potential energy stored in the spring?
Oh, yeah. 1/2
K
x squared.
Let's use d squared because that's how far you've got it compressed. We'll use d instead of
Yeah, if you
x.
guys want to put an equal sign here, but again, we are using d for our distance. So I'm going to put d right there.
And even though it's negative d, when you square it, it'll be positive.
Exactly. Okay. So I also want to talk about if we were going to calculate the work. How do I describe this?
Well, the work done by friction is the force of friction.
The work done by friction. Let me make that W look better. The work done by friction is going to be the force of friction.
And how far is it going?
Well, it's going to go
3D.
Okay.
Work is force times displacement. The force that's slowing it down is friction, and the displacement is 3D.
Okay. All right, I think we have everything on here. Am I missing anything?
And I think we can go ahead and do the graph
This guy
now.
here. Okay, so
I noticed that graph the x-axis is the number line that's exactly the same as the number line on the diagram at the top. Is that not the case?
Excellent observation.
Sweet.
And then what's my y-axis?
That's energy.
Energy. Should I do this one over here?
Yeah, do it over here.
Okay. So I'm gonna go ahead and sketch this out. It's not gonna look great. I'm just kidding. It won't look great.
Yeah, just thank God Mr. Blaken's not doing it.
Okay, and we said that this is increased energy.
Energy.
Okay, energy, and this was just like our
Negative D.
number line, right?
Yeah, negative D, 0, 3D.
Okay. So the first part says A sub I, the kinetic energy of the block. Okay, so
Well, at negative D, what's the kinetic energy?
well, it was at
Zero.
0. So right here, right? That's my
And-
kinetic energy.
And what would be the kinetic energy when it gets to 0?
When it gets to 0, it's going to be max. Does it matter where max is?
Pick a spot.
Right there. It doesn't matter. As long as you're consistent with both kinetic and potential energy.
Yeah.
Okay. So when I was looking at the answer key for this, they said that they're not going to either give or take away points for the way that the line is drawn.
However, the line should have bulged the other way.
Oh yeah, you're right. See, but you wouldn't get points marked down
It's
for
not
that.
gonna
But
make it.
technically it is like
They will
this.
do that sometime, though. Okay.
Yes. Okay.
And then what happens to the kinetic energy from 0 to 3D?
From 0 to 3D, well, it goes from max to 0. So I know that right here has to be right here again, right?
Yeah.
I'm just going to go ahead and connect.
All right, so now we've answered the first one. What's the next one?
Okay. It says, oh, there it is. The potential energy of the block spring system. So at negative D, what is our potential energy?
It's max. Now, the law of conservation of energy says it's got to be the same as the kinetic, so
So this is what they're going to give you points for, making sure that you have addressed the fact that the energy has to be the same at the beginning here for UG and for
because where's that kinetic energy coming from? Out the spring.
Yeah. And now at the at the 0 mark, what is my UG doing here?
0.
Okay, so now it's here, and this one technically is like this,
Mirror,
right?
in mirror image.
Yeah. Oh, so cute. Okay.
I think that's answers the question.
Well, yeah, because we don't have any UG over here, right?
Nope.
Ain't no UG. Okay. All right, moving on. Okay. The spring is now compressed twice as much to delta x, twice as much to delta x at equals 2d. So over here, right?
Yep.
2d. So instead of going here, it's going 2 times
Use
as
a
much.
different color. Right? Use blue and just show it back there at 2D.
Okay. Boop. So right here would be 2d.
All
Okay.
right.
A student is asked to predict whether the final position of the block will be twice as far at x equals 60. So it wants to know if it's going to end up
Twice as far would be 6D.
right here.
So that's what the student says.
Yeah. If you bring it back here, twice as far, is it going to go twice as far this way?
And the student says,
The student reasons that since the spring will be compressed twice as much before, the block will have more energy when it leaves the spring, so it will slide further along the track before stopping at position x equals 60.
okay.
So it says that they're saying that if you compress it 2 times as much, it's going to go 2 times as far.
Okay. And their question for you is,
Their question. Which aspects of the student's reasoning, if any, are correct? Explain how you arrived at your answer.
well, he said it would go twice as far because it has more energy. And I would say that he's right. It's going to go farther. I don't know about twice as far.
Okay, so we'll make a little note. It will go further.
Yeah.
Farther? I have no idea.
We'll go farther.
It will go farther. That totally does not look like it's spelled right, but that's okay. So that was B I. Okay. Which aspects of the student's reasoning, if any, are incorrect? Explain how you arrived at your answer.
Now this is a hard one.
Okay.
Well,
So,
what's incorrect?
well, we know, looking at our equation for a spring, we know that the distance isn't 2 times, it's the square of,
Right.
right? So, I'm a little
Well,
cheat
that's
sheet
right.
here.
The energy stored in the spring varies with the square.
So like this, 1/2 k 2d squared. So if we're pulling it back twice as far, 2d, so it's gonna be 4 USP. And
So it'll have 4 times the energy, not twice as much energy.
exactly.
So 4 times the energy instead of twice as much means it's going to go farther than twice as far.
And where do we get that from? We got it from,
The fact that the energy stored in the spring depends on how far you've compressed it, and it varies with the square of how far you've compressed it.
and correct me if I'm wrong, another way to look at this, there's a 1 here.
Yeah.
One squared is 1, right?
Yeah,
So 1 is 1 SP.
that's an excellent point.
Okay, and this is 4, so we're gonna put 4
Yeah.
right there.
Sweet.
Okay. All right,
What
so
was that question we're trying to answer?
it says which aspects of the student's reasoning are incorrect. Explain how you arrived at your answer. And so the block is not going to go to it's not going to go 2 times as far. Rather, it's going to go 4 times as far.
Yes.
So just to recoup, just to regroup here, if you pull the spring back 2 times as much, it's going to do 4 times as much work. We can't actually know what the distance is going to be yet.
Have you ever popped anybody with a rubber band? If you pull it back a little bit and hit them on the back of the neck with it, don't ever do that, it's going to hurt. If you pull it back twice as far, you're going to make them 4 times as mad when you did it.
That's actually perfect. That's a great explanation.
Ah!
On to letter C. For the 13th time. Use quantitative reasoning, including equations as needed to develop an expression for the new final position of the block. Express your answer in terms of D. Okay. We're gonna take a look at the potential energy stored in the first time that we move the block back
We've
first.
got that already.
Okay, I'm gonna rewrite it right here, and we're gonna call it UG1. Okay, and this equals the work
The first time.
the first time, and we know that work is force times distance, right?
Yes.
But how far was our distance?
3D.
It was 3D. Okay, that's how far we went.
That's the first time.
Okay, now right here, I'm gonna do it right here.
Why don't you do it underneath it?
I can fit under there. So
The
now
second time.
the second time is going to equal the energy that we're going to store the second time is going to equal the work that we do the second time.
Okay, and the work is going to be 4 times the work you did the first time.
Yes, it is.
So don't put W2, just put a 4 in front of the W.
Right here.
There you
Yes. So the work I do the second time is the work I do the second time is going to be 4 times as much as the first time.
Because it's got 4 times as much energy.
Mm-hmm.
So that means that what we've got here,
Okay, it's going to be F3D, but
4 times as
4
much.
times as much. All right, and we got that over here.
Yeah.
Okay, so now what? We know that work 2. This is work. Oh, this is work 2 right here.
Uh-huh.
We know that work 2. I'm just gonna rewrite it right here. Work 2 is going to equal,
Force times displacement, force of friction.
yes, force times displacement. We're gonna call that displacement x2.
Yeah, friction, force of friction.
So that what we're talking about is the amount of work that we did that second time around.
To bring it to a stop.
To bring it to a stop, and we want to know how much distance it went that second time around. So we are trying to solve for this. This is what we want to know.
Yep.
Now, when we let the spring go and it passes our 0 mark, it's dealing with friction.
Yeah.
And that friction is going to have to do 4 times the work to slow it down.
Which we already have right here.
which we already have here. So let's go ahead and plug this in. So we said our force, we're going to say our force of friction times 3D, yeah,
Times 4.
times
Parentheses.
4.
Put parentheses
Oh,
around
right
that.
here.
There
Okay.
you go.
Beep, 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 okay.
So we want to solve, see, you should have a force of friction right there.
Oh yeah, yeah, that right
We
there.
want to solve for x2.
We want to solve for x2, but what do we, the force of friction is going to be the same.
You can get rid of those.
We can get rid of these. Okay, and we're left with
Boys and girls, may we have a drum roll, please?
the distance our second time is going to be
3 times 4.
12D.
12D. Boom, to boom, to boom.
okay. So what we did was we broke this down into the first time we pulled it back and it went go and we let go, and the second time we pulled it back and it let go, and we wanted to know how much further it was going to go the second time. And how we can prove that.
And the bottom line is how much energy is in there, how much work was done. When you pull it back twice as far, because it's squared, you get 4 times as much potential energy. So you got 4 times as much energy in the system, 4 times as much kinetic energy, 4 times as much work needed to bring it to a stop.
And you can see that progression here. The first time the work was force times distance. The second time the work, it's still force times that same distance, but we multiply that work times 4,
That's right.
getting us that 12D. And we ignore friction because we ignore our force because it's just the force of
Well, it
friction.
cancels out.
And it cancels out.
Now, this is hard, notice? And in life, many things are hard, but that doesn't mean you back down away from them. It doesn't mean you can't do it. You got to keep swinging away until the chunk go down.
All right, so after reading part D, there's a lot of letters and numbers in here. There's 2 parts to this question.
Well, what part did he have right? How do we prove the part he did right? How do we correct what he did wrong?
That's what I'm trying to say. Jesus. Okay. So we proved, so one of the parts that he said that was right was that it would go further.
And he was right.
And he was right.
We proved that.
We proved that 12D.
But he was incorrect when he said,
how far it went.
Yeah.
He said it would go 60, and that's a 6. And we said it would go 12D.
he said twice as far, and we came up with 4
4
times.
times as far.
Oh, that wasn't much like pulling teeth.
Whew, done.